pretty awesome looking at the combination or the connection between electricity and magnetism. Of course, this is the basis of, well, every device that we use, actually, relies on this connection. Maybe that's an exaggeration, but anyway, so one of you in the class might be Hans Christian Ørsted, and his principle, his what he came up with and the reason why we study. He's the first one to sort of make the connection that realize that if you had an electric current, you would create a magnetic field. So, and just the motion of electrons creates a magnetic field, an area where a magnet will respond. Okay, he actually proved this as I think almost an accident. It was a demonstration as a teacher, and his thought was that they weren't connected. Back then he thought they weren't connected, and then he found exactly the opposite. By proving one thing, he discovered something much more powerful. And there's a nice little lab with his apparatus, actually, if you choose to do that, really easy. So, for example, if you had a magnetic field, you had an electric current flowing through a conductor. So imagine this thing here is a conductor. It would create a magnetic field that looks like circles, concentric circles, and this is supposed to be a picture of it, right? So this must be a conductor, and someone sprinkled iron filings, and they show, concentric circles moving around it, okay? And that's the magnetic field created around a straight conductor. Now, here's something totally new, the idea of left-hand rules. Because something we care about, and you don't really know why yet, why we care, but just trust me that we care about the direction of the magnetic field. If you remember from the magnets note, I said the direction always points south. So in other words, and in a circle, it's hard to say what's south, but, without getting into the rule yet, see here's the concentric circle, or the circle that sort of represents that magnetic field. And if I was going to draw arrows on it to represent the direction, it would be it looks to me like a clockwise direction. And that means that if you had something like over here, you had a north pole, they would be attracted, right? And that's important, okay? But so how you do this, and this is like very common, these left-hand rules. Imagine grabbing hold, and kind of the picture is pretty good. You grab with your hand, grab hold of the conductor with your thumb following the direction of the electrons. Then your fingers wrapping around point in the direction of the magnetic field. So if you look, this guy's finger here is pointing sort of up, and then it's going to point around the downside of it. So it's following that direction. Okay? So if we're looking for the direction of a magnetic field, that's what it is. Just a quick thing as far as conventions are concerned. This is just so you know by picture what I'm talking about. If I draw this red here, these red dots represent conductors that are pointing into the page. So these would be long cylinders, right? Long, narrow rods, so to speak. But we're only looking at them head on. Okay, and they're pointing into the page. And that dot here represents, if you see that dot, it means that what I'm trying to tell you, or whatever the question's trying to tell you, is that the electrons are moving towards you, towards your face. And if you see an X, the electrons are moving away from you into the page. So just an example, determine the direction of the magnetic field around this conductor. So it's going to be a circle, because I've told you that it's concentric circles. And then based on the direction of the magnetic field below, determine, oh yeah, that's a different question. So first this question, and then we'll do this one here. So here's the solution. You take your left hand, your thumb's going to point into the page, because the X means into the page, and if you do that, you should be doing this as you're watching. Your fingers should be wrapping around that conductor, and they're pointing, like they'd be pointing up over here and down over here. If you're not getting this, by the way, you're probably watching in class. Come ask me to show you, okay? I'll help you with it. Okay, the other example, right here, based on the direction of the magnetic field below, so we know that it's circles, determine if the current is flowing into the page or out of the page. Okay, so here you use the left-hand rule again. Wait a minute. I changed it. I knew something was wrong. I'm sorry, this magnetic field should be pointing down here and up here, which is obviously the opposite of this and not what's on the original page. So if you could fix that. But anyway, the way that I approach this problem though is you grab your left hand, you make your fingers sort of wrap around in a coil, in a circle. Your fingernails are going to point down on this side, right? And then your thumb should be pointing towards your face, right? And that means the electrons are coming out of the page. Okay? So sometimes you see something called a right-hand rule. It doesn't make much sense in practical application because it's all, in anything sort of practically with electricity, we're talking about motion of electrons. So we always use left hands, and you just, the rules that I've showed you, you just use your left hand for it. If you ever saw something that said conventional current or right-hand rule, what that means is there's somebody along the way said, well, I don't know why. Someone once decided that, there's positive current flow, which isn't generally true, right? It's always electron flow. But if you're dealing with conventional current, and so say you knew the electrons are moving from right to left, well, the conventional current would be the opposite, from left to right. It's just the opposite, okay? We don't deal with it very much, but if you do see that term, that's all it means. It's like the opposite of regular electron flow. And if you were going to use one of your rules to figure out direction of magnetic field or whatever, you would use, you do all the same stuff, but with your right hand instead of your left hand. I don't really question that. I don't do that with class. Everything we do is left hand. It's just that if it came up somewhere in further study. Okay, so most of the time, and I will show you this in class, or ask me to show you in class, and hopefully you do some of the labs too, right? Most of the time, we don't deal with straight conductors when it comes to creating magnetic fields because they're not very strong. A coiled conductor is gives you a much stronger magnetic field. Basically, you got just more stuff concentrated, right? So we can follow a left-hand rule to find direction of either magnetic field or current. And just so you see here, what happens on your coil, and again, this is a lab you can do, you can send electrons through it, send a current through your coil, and you'll find out by testing it with a magnet that one side of your coil will be north. Like if this thing becomes a magnet. If you hear the term electromagnet, that's exactly what this is. You send electrons through a coil and it becomes its own magnet, where one end is north and one end is south. And the way that you figure out, without testing it with a magnet, what's south and what's north, is you take the electrons flowing through, right? You take your left hand, you let your fingers wrap in the direction that the electrons are moving through the coil, and your thumb will point north. Okay? Just an example. If you take this one, determine the direction of the electron current on this. Notice I use the word solenoid. That's just another word for coil. Okay, so if you hear the word solenoid, it's just the same thing. So if, for example, I tested and I knew that this was the north end of my electromagnet and this is the south end, and I wanted to know, well, which way are the electrons going? The way that I would do that would, again, take my left hand with my thumb pointing north, and your fingers will point down in this direction, right? Down the front, and the electrons will go down the front, up the back. And so I'll draw arrows to represent the direction of the electron flow. Take this magnet where I know the electrons flow out of the small end, so I know the direction of the electron flow on this one. Now I want to know, is this north or is this north? Which end of my solenoid is north? And so that the way you do that, again, left hand, let your your fingers are going to wrap in the same direction, because if I point, my electrons are flowing out of here, they're coming down, they're going around the back, and then they're coming up here, down the back. So they're all pointing, they're all moving in this direction. So my fingers will point that way, and then my thumb on my left hand will automatically point north. So here's the north end of my coil. If you need help with this again, it's hard because usually when I teach this, I'm teaching it more live, right? So you can actually see my hands while I do it. Because that's not the case, just please ask for help when you do it in class. When you're watching this video, I'll show you what I mean. Oh, great video. This is old school video. I love these videos.
When you're out on the water, it's great to be fishing. But fog does tend to dim your enthusiasm. Don't despair. Your handy compass works in rain, hail, and yes, even fog. Unless, of course, there is something which throws the compass off. In which case, you might be in for a bit of a surprise. A compass needle is simply a magnet. And an attractive force exists between magnets and iron objects, even at a distance and even through the vacuum of space. It's as if invisible hands pull the magnet and metal together. In this way, magnetism is similar to the forces that charged particles exert on each other. These forces act over a distance in the same mysterious way. During the 17th and 18th centuries, electricity and magnetism developed as separate sciences and were believed to be unrelated. Then, in 1800, Alessandro Volta developed a device that paved the way for a change in this view. His device consisted of copper and silver coins, arranged in a column and separated by pieces of cardboard soaked in salt water. When he attached a conductor to the top and bottom, like this, and brought the two ends together, a spark resulted, indicating that a flow of charge was occurring. Volta's work eventually led to the development of batteries, which could be used as sources of continuous charge flow. A battery like this was used by Danish physicist Hans Christian Ørsted in 1819 to conduct an experiment in which he hoped to prove conclusively that electricity and magnetism were not related. At first, the demonstration seemed to work. When the switch was closed, the compass needle, which was perpendicular to the conductor, didn't move at all. However, when Professor Ørsted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Ørsted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Depending on which way the negatively charged electrons flow through the conductor, the magnetic field around the conductor will be in one of two directions. With the electrons flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well. Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around the conductor, with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately. What happens to the overall shape of the magnetic field if the conductor is bent into a loop? Let's turn the current on again and find out. We apply the left-hand rule at different points along the conductor. We can map the magnetic field around the loop. Notice that the shape of the field resembles a donut. But if a number of identical loops are added, the resulting figure is called a helix or coil. Looking at the coil in cross-section, we'll represent electrons flowing away from us as X's. And here at the bottom, electrons flowing towards us as dots. Applying the left-hand rule for conductors to each turn of the coil, we can begin to build a picture of the magnetic field around the coil as a whole. Since the distance between the turns of the coil is very small, we might think that the fields would overlap like this. But this is not the case. Magnetic fields do not overlap. Instead, the field of one interacts with the field of the other to produce a combined field like this. If we examine the area between two of the turns, we can see that the two interacting fields effectively cancel each other. This field interaction occurs between each of the turns of the coil, resulting in an overall field which surrounds the turns and resembles a somewhat flattened oval. The same oval pattern is produced at every point around the coil. And it's the merging of all these ovals that forms the magnetic field for the entire coil. Since the field direction of each oval is the same, then in the center of the coil, cancellation does not occur, and that portion of the field is very strong. There is also no cancellation outside the coil, but because the field is spread out, it is much weaker here. The relationship between the direction of electron flow in the conductor and the direction of the field in the center of the coil is given by another left-hand rule, the left-hand rule for coils. This time, the fingers curl in the direction of electron flow, and the thumb points in the direction of the field within the coil, or to the end of the coil that acts as a north pole. The fingers curl with the current, and the thumb points north. If we compare the magnetic field of the coil with the field of a bar magnet, we can see that the shapes are nearly identical. Each has a north and south pole. But an ordinary iron bar has no magnetic poles. What then happens if we insert this bar into a coil with current flowing through it?